I will describe dSpace. This is a framework to simplify smart space development. Shipments of IoT devices have tripled in the last 5 years. It's estimated that there will be more than 13 devices per person on average in the next 2 years, from smart lights to voice assistants and robots. These devices are transforming our living spaces, so it's important to have the right system support for building smart space applications. There has been a lot of progress in terms of both research and industry for enabling smart spaces, but it's still tedious and complex to program smart spaces, especially with a greater variety of devices and use cases. In today's smart home products, for example, we are still writing apps over low-level device-centric APIs, such as programming turning on this lamp and that vacuum, as opposed to, say, turning on this kitchen or house. We are writing monolithic apps over these low-level APIs, and then we are configuring policies as flat files of these if-then-that rules. These policies can be complex to manage, to reuse, and to reason about as the number of devices and use cases increase. So how should we address this complexity? In system research, the well-established approach to simplifying development and improving developer efficiency is via modularity and abstraction. So in dSpace, our goal is to find a minimum set of abstractions to achieve modularity in smart spaces. In this talk, I will tell you how dSpace achieves modularity both by design and by examples. To begin with, here is a smart light bulb, which is common in today's market. In dSpace, we abstract away and represent each physical device as a digivice. Where internally, each digivice has a model and a driver. The model is a set of attribute value pairs that can capture the device's intended states and its current states. And driver, that is a piece of code, will take action, make the target states happen. For example, one can set the intent of the lamp's power to be on, and then the lamp digivice driver will configure the physical lamp to turn it on. Once done, the driver updates the model to reflect the new lamp states. As we will see next, digivice as an abstraction is flexible in the sense that it can configure both physical devices, aggregates of devices, or virtual devices. So now say we have multiple devices. They can have different features and come from different device vendors. We can represent them using different digivices, where each digivice driver can use different device libraries, programming languages, and their models might also be different. Notice that such heterogeneity can lead to complexity. For example, one digivice refers to the lamp's power as attribute power, whereas the other calls it turn on and as a Boolean value. This is undesirable because whoever is interacting with the lamps need to deal with these heterogeneous APIs. To address this, dSpace allows developers to create universal digivices that can configure those device-specific ones, just as a lamp digivice configures the physical devices. A universal lamp driver can configure a lamp of either type, and yet it exposes a uniform model. Now to achieve this, we need to configure a universal digivice and a device-specific digivice. dSpace does this with its composition primitive mount. Briefly, mounting a digivice to another digivice, which we refer to as the parent, allows the parent to write to the intent of the digivice being mounted, and read the status and the other events from that child digivice. In other words, mount allows the parent to control the child. Mount can have different semantics. Let's see some more examples. Now we have two lamps, so we want to configure them in aggregation, like configuring the brightness of the entire room instead of individual devices. A natural way to do so is to introduce a living room digivice that mounts both lamps as its children. Doing so allows user to configure the room level brightness. The room will translate this brightness level to individual lamps. As a simple example, given two lamps mounted to it, the room will divide its intended brightness 0.8 by 2 and sets L1 and L2 accordingly. Notice that given the lamp digivices and the universal lamps, the developer of the room digivice doesn't need to program the physical devices. They can just reuse existing digivices. In fact, we don't have to stop here. We can keep on raising the level of abstractions and create high-level devices when doing so makes sense. These devices form what we call a control hierarchy, where the user can simply program the intent of the high-level device, and this intent will propagate downwards towards the physical devices. And then the events from the physical devices will propagate upward towards the higher-level devices. Let's see a different scenario. Now say we have a Roomba robot vacuum and a camera in the living room, and we want the robot to pause when there are humans in the room. This can be done by running object recognition over a video stream and controlling the robot accordingly. So this requires us to integrate data processing capability with devices. And dSpace does so with digidata. Digidata also has a model and a driver, where the model has data input and output attributes, and the driver runs data processing to transform the input to the output. For instance, here in the CV digidata, the driver reads from the input a URL of the video stream and writes the objects the ML algorithm detects to the output attribute. So to use the digidata, we simply mount the CV to the room device. The room's driver can then write the URL of the video stream it obtains from the camera to the CV's input and read the list of objects from CV's output. Now, what if we want to pre-process the video before sending it to CV? To do so, we can add a new video processing digidata FF and use pipe primitive to compose the data flow to CV. The pipe will write the FF's output to the CV's input. Now going further, say here is a living room and here's our kitchen. What if your robots move across room, say from living room to the kitchen? We don't want the presence of the human in the living room to stop the robot in the kitchen. And in some sense, different rooms, they may have different robot policies. In dSpace, the device can be mounted to multiple parents, but only one parent can have write access to the device. So when the robot moves from living room to the kitchen, it is yielded from the living room and the kitchen is unyielded. We can use these features to delegate devices to third party. Say your living room and kitchen are mounted to the house device as well as an emergency control from the city's fire department. Note that to achieve correctness, dSpace will ensure the resultant topology to be a multi-tree to avoid any mount loops. One can then define a policy that says if smoke detector in the kitchen is triggered, yield the room from the house and make the emergency controller the active parent, which can then configure the room accordingly. More information about policies can be found in the paper, including how users can customize how intent conflicts are handled. So to recap our design, departing from device-centric abstractions, dSpace provides a small set of abstractions, including modular building blocks, device, and digidata, that can be composed with primitives mount, pipe, and yield. And one can customize them through rich choice of policies to achieve scenarios such as mobility and delegation. Further, dSpace runs devices and digidata in a microservice architecture, and it does so by extending Kubernetes control plane. Let's see how this is done briefly. Kubernetes is a widely used container orchestrator for data center automation. It has an API server that keeps cluster states as key value pairs, and a set of controllers and CLI that interact with the API server to manipulate the cluster states and to perform, say, scheduling. Applications in Kubernetes are run in units called pod, where each can be seen as a microservice. For dSpace, we deploy the drivers of digits as pods and keep their models as objects in the API server, and implement controllers and CLI that are useful for dSpace operations, such as ensuring the correctness of composition. You can find more information about the design and implementation from our paper, including a summary of design principles, runtime architecture, and the implications on security as well as evaluation. We implemented 10 scenarios in smart home with dSpace. where we integrate 9 real-world devices. We showed dSpace can support all scenarios easily and require less than 300 lines of code. Compared to dSpace, the existing frameworks either cannot support this scenario or will involve substantially more code. We validate the ease of use of dSpace through a user study, and our performance benchmarks suggest the dSpace runtime adds less than 20% of the latency overhead. With that, thank you.